Okay, so welcome back to another video. So here we have a nice little number theory problem. We want to find natural numbers and satisfying the following expression below. We have 1 factorial plus 2 factorial plus 3 factorial all the way up to plus n factorial such that the following expression results in a perfect square. 1 square, 2 square, 3 square, etc., for that extension. So one method that's a common method everybody might, start off with in the initial process is we would actually like to start off with each natural number. So check for 1, 2, 3, 4, 5, etc. And you can do that, but that's just going to result into a little bit tedious. And remember, we're actually doing with the entire natural number system. So you literally have to check every single number from that system, which we're going to be here forever. But there's actually a nice way, a little shorter way on how to do this, which is very interesting. That's actually going to involve a little bit of some modular congruence that you learn in number theory and even in the introduction to proofwriting classes. So it's correct that, yes, we will be actually just checking a couple numbers, but then the second step afterwards is we're actually going to make a nice little claim and proof to that such that the rest of the following numbers actually do not form a perfect square from that expression. So that out of the way, I actually gave a little bit of a spoiler on, you could probably guess where we're going with this, but why don't we actually just jump right in and see what happens. So the initial step, why don't we actually start off with n is equal to 1 of the natural numbers. So n is equal to 1, so then that would have to imply that I have 1 factorial, which of course is the same thing as equal to 1, which of course is the same thing as 1 square. So that leaves a check. So if we try n is equal to 2, so that means I have 1 factorial plus 2 factorial. So 1 plus 2 times 1, so that's 3. So that means this does not form a perfect square, so that's out of the way. So n equals 2 does not work. So n equals 3, let's try that. So I have 1 factorial plus 2 factorial plus 3 factorial. So that means 1 plus 2, so that's 3. And then 3 times 2 times 1 is 6. So that means 3 plus 6 is 9. And so that's the same thing resulting as 3 squared. So we have 2 numbers in our natural number system that actually works for satisfying the following expression for a perfect square. So you will have to keep going forwards for n is equal to 4 and then so on and so forth. You can actually do this one by one if you want to, but we're not here to do that because the video would be super duper long if that was the situation. So the claim I mentioned is what we're going to do is now checking for n is equal to 4 and then everything upwards. So 5, 6, 7, 8, 9, 10, etc., all the way up from n is greater than or equal to 4 in other words. We're going to actually make the claim and say that it does not form a perfect square such that n is greater than or equal to 4. And so the modular congruence, modular arithmetic comes in handy with this supporting this situation over here. So we want to prove, so let me actually first write down our statement, our claim, what we want. Well, here's our statement, our claim, 1 factorial plus 2 factorial all the way up to n factorial. It is not a perfect square for n is greater than or equal to 4. And so the proof actually is interesting that a perfect square can actually come into 3 different forms. And specifically the 3 different forms that I mentioned is that we're actually going to be using as the modulo 5. So whenever you divide a number by 5 and then you get your following remainder. So we have that. So let me first write the proof of this. So the proof I have is starting off, it says a perfect square is in the form of 0 mod 5, 1 mod 5, or 4 mod 5. So you might be thinking, how's that possible? So we can actually try out these numbers. So we can actually start, for example, in a form for 0, for example. So 0 square, and even though it's not in the natural number system, but you can actually see why it's in that form. So 0 square is actually in the congruent form of 0 mod 5, since if you were to divide 5 under 0, you still get 0 and you get the remainder of 0. So that's fine. Okay, so 1 square, that's going to be 1, of course. That's congruent to 1 mod 5, since if you divide 5 into this, you still actually get a remainder of 1. So why don't we try now 2 square? So 2 square congruent to now that's going to be 4 mod 5, since that's 4, and then divide 5 into that, you still will get the remainder of 4. So why don't we try another number, 3 square. So 3 square is 9, right? So what that means is that we actually get, it's the congruence of 4 mod 5, since 9, if I were to divide 5 into that, it can actually go into 9 once, but you get a remainder of 4. And let's try 4 square, so 16. That is actually congruent to 1 mod 5, since if you think about it, 16 divided by 5, so we know that 15 is divisible by 5, that can go into 3 times, but you get a remainder of 1 from that. And let's try one more number, 5 squared, so that is 25. And so 25 divided by 5, it goes into it 5 times with a remainder of 0, so that means it's 0 mod 5. And so we can actually see the picture, etc., etc. We actually have these formed in a perfect square, 0 mod 5, 1 mod 5, or 4 mod 5, either one. So with that being the case, so now let's actually get on to moving on for n is greater than or equal to 4. So then that means following the expression, so 1 factorial plus 2 factorial plus 3 factorial plus 4 factorial plus 5 factorial plus all the way up to plus n factorial. So what we do is, even though we're actually going to consider dividing this by modulo 5, of course. So that's actually congruent to say that even with 1 factorial plus 2 factorial plus 3 factorial plus 4 factorial, and that's when we stop, since everything from upwards to 5 can still be, we can get either our remainders of the form. So now mod 5, and then crazy enough to see that, interestingly, that if this doesn't convince you, so why don't we actually check out the numbers. So 1 factorial, that's 1, plus 2 factorial, so let's see, that's 3, so plus 6, that's 9. So that means plus 24, that's going to be 33. So if I add a 5, so that means that's what, 120, and then that means add that, so that means that's going to be 153. And if you were to divide that by 5, it can still go into that, let me see, 120 times 5, that's... It can still go into it 24 times, but you still get that remainder of 33 from that 153. So, because if you see that everything here, if you add all this up, this actually gives us 33. And so, even if you continue on so forth with 5 factorial plus 6 factorial, you can still get that remainder of the 33 each side. So that actually follows that congruence. So in other words, that means 33 mod 5, even though if you were to divide 5 into 33, it can still go into it, you're still going to get a remainder of 3. So this is also congruent, equivalently congruent to 3 mod 5, which of course that stops there, and that actually ends the proof, because as mentioned, a perfect square actually has the following for 0 mod 5, 1 mod 5, and 4 mod 5. Here we have a 3 mod 5. Let me box this just to emphasize this. We have a 3 mod 5 over here, which does not satisfy the perfect square that we are actually achieving for. So therefore, we actually just complete the proof. So I'm just gonna just mark this off. So therefore, so put in the 3 dots, 1 factorial plus 2 factorial plus 3 factorial all the way up to plus n factorial is not a perfect square for n is greater than or equal to 4. And so that actually ends that off. So just mark the second box because that completes the proof. And so therefore, our only 2 numbers that actually satisfy the following expression is going to be n is equal to 1 and 3. And so therefore, that completes our expression that we want to find for the natural numbers n. 1 and 3, you just plug in, and we already did that check. Anything greater than or equal to 4, we actually just follow with the proof that for the perfect squares in the following form. And then we actually check with the modular congruence to actually, get to that emphasis to see that this does not follow once you actually put in the expression over here with the congruence. There you have it, and just the 2 numbers, 1 and 3. So yeah, that's pretty cool if you ask me.